I have. Okay. Yeah, okay. Well, good afternoon, ladies and gentlemen, dear colleagues. I hope you enjoyed your lunch and you are strong enough now to survive the afternoon. I am convinced that you will survive because we will have another good and interesting presentations. And the first, I would like to give a short introduction. First presenter will be Professor Maria Teresa Rasolini. She holds a master's degree in environmental sanitation from the University of Presbyteriana Mackenzie, and she has a PhD in public health from the University of Sao Paulo. She is currently an associate professor in the Department of Environmental Health at the School of Public Health here in Sao Paulo, University of Sao Paulo. And her current research interests in the area of research are in the area of environmental microbiology, and in this area especially in the evaluation of the microbial quality of waters and quantitative evaluation of microbial risk. I would like now to invite you to come to the floor. The floor is yours, and she will report about the evaluation of water quality and health implications using microbial risk assessment. We have for each presentation 30 minutes, and after 25 minutes I will show you a piece of paper. That means 5 minutes are still left. So this is only just to keep the schedule, and so I think you agree. Okay, the floor is yours, please.
Thank you. Thank you so much. So, good afternoon. First of all, I would like to say that I'm very happy to be here and to have this experience, to share experiences with you. So my talk today, it's evaluation of water quality and of health implications using microbial risk assessment. I would start referring to the large outbreak of cholera occurred in London in 1854. This large outbreak, I think, showed us a lot of things. First of all, how to analyze and how to make associations with living conditions, environmental quality, and health outcomes. And it shows us that it's important to be aware to route of exposures, because some of the pathogens we are exposed comes from the environmental. And then we have to be aware in reducing risks. So that's what this large outbreak showed us, and we have to learn from this. Still nowadays, waterborne diseases outbreaks are public health concern. And still now we have to face some etiological agents. And here are some of the most common etiological agents that implicated of waterborne diseases outbreaks. So, and we can see here there is a lot of diversity, a lot of kind of microorganisms like Cryptosporidium, norovirus, or Shigella, or Campylobacter. So it's a real concern. And as I mentioned before, it's linked to social and economical drivers. So I would highlight the lack of access and improved water, social inequality, degraded water sources, unprotected water sources, and the scarcity of water we are facing nowadays in our state, as we could see in this morning. And all these factors lead pathogens into the water sources, including the emerging and re-emergent pathogens. Whoops. And it's not a regional concern, but a global one. And we can see this when they see the goals issued by UN, the Sustainable Development Goals, where there are many goals related to water. So, especially goal 6, is specific for water, for quality of water, and which is to ensure availability and sustainability management of water and sanitation for all. But it's not only the goal 6 is related to water. Some of other are concerning water too, like goal 3, for example, which states that the end of waterborne diseases, or reduce the number of deaths and illnesses from water. Or goal 12, that states the good management of waste in order to reduce water pollution. And the goal 15, which brings us the importance to conserve and restore our fresh water. And several publications have been publishing about this issue. So about the emissions of some parasites into water sources, or the outbreaks associated with drinking water sources. Here, it's a perspective of Latin America and waterborne protozoas, the occurrence of waterborne parasites. And finally, this one, it's about the waterborne transmissions of protozoan parasites. It shows us that it's a very concerning issue, and maybe you have to look more carefully to our surveillance models, and maybe find some new approaches to deal with this impact of environmental quality on health. So, and especially those tools that allow us to explore scenarios, to simulate scenarios, and then maybe see a little bit ahead to act in the present. So, and when we are talking about scenarios are not simple. Most of the time, they are very complex. So a tool that you can make a zoom and extract some important part and see how to manage with it. It's very important. It's a valuable tool for planning. So I think the risk assessment is a valuable tool for this purpose. This risk assessment can help us to cope with these complex scenarios, allow us to explore scenarios, simulate scenarios, evaluate intervention measures. So it's very, in my opinion, is a valuable tool for managing water quality and its impact on human health. But for this, we have to formulate questions. Yeah? Specific questions. And when we are applying to risk assessment, I think you have to formulate these specific questions. And for example, here there are some examples. For example, what level of risk people living in irregular settlement are exposed? We know that water supplies in some places are not adequate. Or what is the likelihood a child will get sick with an infectious disease from swimming in a contaminated lake or beach? Another one, what's the impact on the water supply chain after an extreme event? And the list goes on. It depends on our objective. It must be clear for applying risk assessment tool. So, but for conducting a microbial risk assessment, you have some steps to take. And the first of them is hazard identification. In this step, we are going to describe our microorganism of interest in a detailed way about its virulence, interactions with host and microorganisms, not forgetting the sensitive population as elderly and children, for example. So routes of transmission, disease endpoints, and a crucial data are epidemiological data. Not always available, but if you have this data, use it, because it's very important. And then we have the exposure assessment. Here, we are going to see the affected population. Again, don't forget the sensitive one. And specify the exposure via intensity, frequency, duration, and duration of exposure. But this step requires from us discussions, research, searching experts, because it's crucial for evaluation of risks. And then, again, we need some data. And then, here are some examples. How much water will the child ingest over a period of time? Or how much will the population eat a specific food or vegetable? Is the pathogen traveling for a source? Is there die off or grow while the pathogen is in the environment? What's the concentration of pathogen in the water at the time of ingest? And the list goes on. So what I want to show you is that the scenario is specific, and so the questions arise is specific too. Do you have answers for these all questions you need to do? No, we don't have. So we have sometimes searching the literature or make some assumptions. But the crucial thing here is to be transparent. It show the assumptions made, where the data comes. And then to be open to review again if it's necessary, if new data appears. So this is a core of the risk assessment evaluation. And then, for microorganisms, is dose response assessment. In this step provides us a quantitative relationship between the adverse effect and the level of microbial exposure. Usually, you take this data from literature. And then finally, risk estimate. Here, we are going to calculate the risk, the probability of infection, probability of disease or death. You know, exposure assessment, you obtained the dose of exposure. Now, when we integrate everything together, we are going to have the probability of the health outcome we are looking for. Tolerable risk. Some countries, they have a tolerable risk established, like the USA, where EPA, the Environmental Protection Agency, recommends that the risk of infection must not be greater than 1 in 1,000 infection annually. The same level has been adopted by the Netherlands. And WHO are using burden disease, like it's not must not be exceeded 1 in a million per person per year. In Brazil, we don't have this tolerable risk, set this tolerable risk. So for comparison, we use the EPA's recommendation. And I take part of a group that you have been studying pathogens in environmental. So we quantify pathogens in some environmental matrices like drinking water, reuse water, sewage sludge, sediment. And the pathogens we are working on is in Giardia, Cryptosporidium, some pathogenic strains of E. coli, Salmonella, Ascaris, and some enteric virus. And then you use this data for assessing risk and see how the contamination of the environmental are affecting the exposed population. So I selected some studies to share with you. So this one is about the quantification of Giardia in crypto in water supply. And we find a high percentage of Giardia in crypto in this water supply catchment. So Giardia was the frequency was 83.3%, in Cryptosporidium 37.5%. And the concentrations were high as well. So Giardia, we found concentrations ranging from detection limit to 8.6 cysts per liter, and Cryptosporidium from detected limit to 2.0 cysts per liter. And we genotyped this isolate. So, and we find Giardia intestinalis and Cryptosporidium parvum and homines, indicating entropic contamination, since they are the genotypes able to cause disease in human beings. And for the scenario, the exposure scenario, you considered the concentration of pathogens in water, in hot water, just before the drinking water treatment plant, and then the reduction logs of these pathogens during the water treatment process, the ingestion rate for adults and for children, and applied the dose response model for which is specific for each pathogen, and then calculated the risk. So for Giardia, the mean risk for adults was 1 in 10th minus 2, and Cryptosporidium 3.9 10th minus 3, which is above the EPA's recommendation, 2 and 1 log, respectively. And for children, we found risk above the EPA's recommendation to 1 log above this recommendation. In this one, it's another study that we assessed four catchment points in the state of São Paulo. And this area comprises 58% of population of São Paulo state and 13% of the Brazilian population. So it's a dense area. And we found Giardia in crypto again, and all of the sources analyzed. And then we applied the same scenario of exposure and find these values of risk. So it varied from 1.42% to 2.59% for adults and for Giardia, and for crypto, again, 0.05% to 0.17%, again above the limits recommended by EPAs. And for tube, the same. High risks were found. And here again, we studied 2 water sources, Guarapiranga reservoirs in São Lourenço River, that Professor Mônica Porto showed us today, that it's a promising water source for supplying water to São Paulo. So we applied the same scenario of exposure, And then, but this time we evaluated virus, risks of viral infection. And then again, we found high risk values. So adenovirus and hepatitis A showed the most, the highest risks we found, and both for adults and for children who have found high risks. And this one is we analyzed 128 surface samples in 11 catchment points distributed of São Paulo State, and then we found high percentage of frequency positive samples for Giardia and for Cryptosporidium in high concentration, reaching 17 cysts per liter for Giardia and 11 oocysts per liter for Cryptosporidium. And again, the genotypes that can cause disease for a human being. In this case, we are working on the exposure scenario, because you have different characteristics among the sources. So we have to look it over and then calculate the risk. So, and this one is just to show you the variability we found among the sources we had analyzed. So I think it's clear that quantitative microbial risk assessment can guide us towards to set targets based on health. For example, public health goals in burden of tolerable diseases. Water quality goals, which means that we can set standard values for water quality. Evaluate systems, reduction factors, for example, for specific treatment to reduce parasites in treated water, in finished water. The QMRA are recommended by WHO for elaborating water safety plan and to evaluate the specific technology for treating water. So I think this is a valuable tool for this purpose, and I think using these you can contribute for achieve the sustainable development goals. Okay, thank you for your attention.
Yes, thank you very much, Professor Razzolini. And well, I think this outcome of your research shows us very nicely that there is, when I look to the risk potential, and you showed us some areas where this risk is quite high. I mean, above 10% is always better is zero, yes. Very high. Well, I think this should be open the eyes of water authorities. We are doing some risk assessments very often and very nicely, and we have a lot of data. But this morning we learned that in Brazil, but also in other states, wastewater treatment is missing. Yes, and that is you are calculating now the risk, and now it's up to the politicians in the end. Otherwise, how to make a change? How to reduce the risk? We cannot only reduce the risk that we know that there is a risk. Yeah, so we have actively to do something. So thank you very much.
Thank you.
Any questions, please?
No.
Or shall we have these three?
Yeah.
Let's go through these. Okay.
I think maybe it's better to
Yeah.
organize the three sections
Okay.
and then
Okay.
for questions.
Okay.
But it's up to you.
No, it's okay for me.
It's okay. So then let's collect the questions, and we can have then the panel and the collection of the to answer the questions later. Okay. So.
I use it.
Questions or later. Well, you can ask the questions later. Yeah?
Yes?
Okay?
Okay.
That's better. Okay, thank you very much.
Okay. Thank you.
So we're coming now to the next presenter. It's Professor Isabel Dueterrelo. I hope I spell it.
I'm here.
Oh, sorry. I spelled your name rightly?
Yes.
Okay. Professor Isabel Dueterrelo is an engineering and physical research fellow at the Civil and Structural Engineering Department at the University of Sheffield. And her main research interest is in the area of environmental sciences and applied microbiology. Throughout her scientific career, she has worked in different microbial-related projects and in multidisciplinary, internationally recognized research groups.
Yes.
Her interest, special interest, is in microbial ecology, and she started this work during her when she was a student at the university in Madrid.
Yep.
That's right. Yeah, she joined the Penny Water group at the University of Sheffield in 2011, and since then she has worked on EPSRC-funded projects, especially studying in different aspects of the microbial ecology of drinking water distribution system and its adaptation to climate change. So that's a variety of interests, and but not nevertheless very focused. And she will report about microbial pollution of water sources under global climate change, implications for public health. The floor is yours, please.
Okay, thank you. If I talk like this, can you hear me? Because I need to move. I cannot. Okay, that's good. So
you can take the mic.
Yeah, okay. Better with the microphone.
Yeah,
then.
better with
okay.
the mic.
Okay. So basically, I already been introduced, but over now it's been 20 years that I've been working in microbiology with archaeologists, with ecologists, and now for the last 8 years, I'm in a civil engineering department working with civil engineers to try to tackle climate change effects. But I'm specialized in pipes. I'm going to explain, it's a fascinating world. You will see now. I'm working in drinking water distribution systems and the effect and the impact that climate change will have in these systems. But I've been already introduced, I'm not going to talk about that. Drinking water systems. Not a lot of people think about this, but there are kilometers and kilometers of pipes, most of them really, really old. At least I'm working in the UK, but in the UK we still have cast iron pipes, we have some lead pipes, all sorts of very old pipes from Victorian times, and we have all sorts of microbiological problems associated with this very old leaking infrastructure. So I'm going to talk about the microbial risks associated with urban water infrastructure, okay? But for me, I'm a microbiologist, even if I'm working with civil engineers. And for me, these are fascinating ecosystems because there is no light, there is almost no nutrient. You keep a chlorine residual and they don't care. They are happily living there. And I can tell you that the diversity of microorganisms is amazing inside the pipes. And the problem is, for engineers at least, is that they can change the quality of the water. They can promote problems of discoloration, odor, taste of the water. They can affect hydrodynamics without the pipes, but also they can be promoters of corrosion. But for me as a microbiologist, the most important thing is they can really affect public health, obviously, because at the end of the day, it's drinking water and the people will drink whatever is transported in these pipes. But for me, again, most of the people, when they think about drinking water, they only think about the water. But most of the microorganisms that live in these systems, they are not in the water. They are attached in the pipes forming biofilms. And more than 95% of the microorganisms that we can find in the systems are happily living attached infrastructure within the pipes. And the problem that we have is, this is a pipe, okay? This is to prove that I'm not lying. It's a big pipe that is going to distribute water then into smaller pipes. but it's how clean they are in the UK. This is a UK pipe, okay? But, I don't know. But yes, for me it's a fascinating ecosystem because even without nutrients, without no light, we can fight fungi, bacteria, protozoans, viruses, all sorts of microorganisms, but they love to live attached to the pipes, again, forming these biofilms. I guess that you are familiar with what a biofilm is. Are microorganisms attached to surfaces that they form like a consortium somehow. And they are very successful because they are protected against the action of disinfectant, chemicals, whatever. They are indestructible somehow. And the problem in an engineering way of thinking is if you have these biofilms attached, okay, we are safe. But within the pipes, which are not perfect, we have changes in pressure, changes in hydraulic regimes, and all that material, it can be mobilized and people will drink it. And this is the kind of risks that I'm looking into. And drinking water sewage systems are very challenged to study. So I'm glad that I'm working with engineers because they can devise, they can design all sorts of devices to try to study these biofilms and the problems that they cause. So we kind of install devices to sample biofilms with coupons in real systems. We also go at night and flash pipes. Because if you do that during the day, the people freak out. So we go out now, we flush the pipes and we collect all the microorganisms that are attached inside there. And in terms of how we analyze the sample, I'm using also the standard methods that are the water companies and the governments around the world are obliged by legislation to do. But I'm going to tell you later that I don't really like those methods. There are better methods to characterize microbial risks in these systems. And my favorite method is DNA. I know it's a bit expensive, but the amount of information that can give you is amazing. From 1 liter of water from a swab within a pipe, all of that is amazing. And this is what I'm telling you, why I don't like the old methods, all these E. coli, heterotrophic plate counts. I don't really like them. These methods are more than 150 years old, and I don't really like them as a microbiologist. First of all, because most of the new emerging waterborne pathogens that we can find in distribution systems, they are not associated with the presence of these indicators. So I think that we are really missing information. The second reason why I don't like them is because culture-dependent methods, which are the traditional methods, they only represent less than 1% of the total microorganisms that you have in your samples, in an environmental sample. Translated means that we are losing more than 99% of information of other microorganisms that by law, by legislation, what the legislation make people do, we don't get that information. So the solution is DNA. I know this method is a bit expensive, but I think it will become cheaper. And for me, this is the future, to track microbial risks in drinking water systems or any kind of system, urban water systems. And I've been looking at biofilms now for 8 years, 7, 8 years. And I look using the microscope. I've been using all sorts of techniques. And for me, it's fascinating that it's a very fast process. Once the cells start, or these microorganisms go in the water and start to attach, in only 3 weeks, you can see that the coverage of this biofilm is triplicated. So it's a very fast problem, taking into account that we are talking about a very tough environment for microorganisms. And this is how they look. I always show pictures because I work a lot with water companies. And if I don't show them these kind of things, they don't believe me. They need to see. So this is one of these first microorganisms that comes floating in the water, and it's going to attach on the pipe surface. It makes the pipe surface more attractive because they are able to produce like sugars, and more bacteria are coming. And these things start to grow, and start to grow. And this is what you have in an experiment in a drinking water pipe in the lab, from a biofilm that is only it's a baby biofilm. It's only 28 days old biofilm. So imagine the amount of microbial biomass that you have in real pipes, in real life. So for me, it's a very big risk that, to be honest, the people don't talk about these things, just the water, nothing else. And as I said, I'm not going to go into details, but my favorite technique, because it's been giving me a lot of data, is the use of DNA, use of molecular techniques. And I'm going to give you examples of how these DNA or molecular methods have helped me to understand better how these systems work. Because at the end of the day, I'm working with engineers, and they always ask me, so what? What we do with this? How can this information help us to improve our drinking water system? So one of the results that we have from experimenting with water and biofilms, this is a system that we have in Sheffield to study water and biofilm. That is a high-density polyethylene, which is the main material that they use in the UK for the pipes. But what we saw is that what grows in these are results all from DNA. But the important thing from this graph is like whatever is growing in the biofilm is completely different from whatever is growing, is transported in the water. So by legislation, we only take samples of water, and you are ignoring the biofilm, you are ignoring the risks of all these microorganisms attached to the pipe. So for me, this result was quite interesting, because most of the people think that whatever is in my water, it must be attached to the pipes, and it's not right. More results. We were flushing pipes near Manchester in the UK, and we were looking at differences between cast iron, plastic, because there is also this belief that plastic is better, and it's not true. Plastic was different. We found different microorganisms living in the plastic and different microorganisms living in the cast iron pipes. And the problem with the cast iron pipes is you have iron bacteria that love to be there. So they use the iron, they metabolize iron and manganese, and for the water companies, these bacteria are a nightmare because they are also resistant to chlorine. So for the water companies, this is a very big challenge, how to eliminate the risk of these biofilms and these incrustation tubercles form in pipes. We also wanted to compare a supply system with groundwater because, again, this is the belief of the groundwater is cleaner than the surface water. Again, it's not necessarily true. And the problem is with the groundwater, they almost not treat it. They put only a bit of chlorine because they have this assumption that it's cleaner. And I can tell you that we found, we found all sorts of, I'm talking about the UK, Europe, okay? And look at all the different microorganisms that I'm finding there. But what we also found is when the flow conditions, this is a graph with the flow conditions in the two sides. And it's not, I guess that you cannot see, but the green side has a very low flow. And what we saw is when you keep a very low flow in your pipes, you promote the presence of only one type of microorganisms, which is Pseudomonas. And I only found these Pseudomonas in everywhere, but stagnant water and very low flow was promoting this kind of microorganism in the pipe. So all of this information is useful for engineers because that way they can control hydraulic regimes or how they manage the system somehow. And we also did with Miller is going to talk after me, a short study, a small study in Cali, in Colombia. And we did the same. Miller's student, Carolina, was, when the water company was calling her, hey, come, because we are, when they swap pipes, when they repair or change pipes, she was going there to, to take samples of pipes and see what was growing there. And she was like, wow, it's amazing, all the different microorganisms. I think she even told her family, don't drink water anymore, because, but anyway, you need to do more tests to test, to be sure before you scare people that you have all these things living in the pipes. But now what I'm doing is I'm looking at all the genes. What the results I gave you before were for marker genes. I was looking for bacteria, I was looking for fungi, but what I'm doing now is to analyzing all the genes that are in our systems. And I'm finding a lot of antibiotic resistance bacteria living, very happy no, I don't know if they are living, but the genes are there in the biofilm. And for me, that's scary because as far as I know, the water companies, they don't treat antibiotics, hormones, all these new chemicals that we have in the distribution systems. So in the project I'm working these days, I'm trying to find out how climate change will impact all these pipes, all these microorganisms and all these pathogens that might live in our distribution systems. And they are going to be affected. They are going to be affected by new levels of contaminants. As I said before, probably antibiotics, hormones, all these new chemicals that they go. We are drinking all of this at the end of the day. Changes in environmental conditions, increases in temperature. I'm sure in the UK the temperatures are not very high. But if we climate change, we have temperatures, increases in temperature, the bacteria are going to love it, I'm sure. And we will have more growth of biofilms. We will also be forced to mix water of different qualities because the good quality water is finishing. At some point we are going to need to reuse or mix water of different qualities, and we don't really know the consequences of that for public health. And I'm always saying that the water companies, they need to change the way they do things, because whatever they are doing now, I don't think it's going to work in the future. So we need to make them change the way they think. Again, for me, one of the most important problems is the antibiotic problem. I guess that all of you are familiar with this antimicrobial resistance. Antibiotics don't work anymore. And I did find antibiotic-resistant bacteria in our water, at least in the UK. Pathogens. I'm sorry. But I think that will make us stronger. What can I say? And pathogens. The main problem with pathogens, if you are young and healthy, I guess that you will have diarrhea for a couple of days and you will be fine. The problem when you drink contaminated water is for immunocompromised people, children, elderly people, people with cancer, with AIDS, because they have an immunocompromised system. So for them it's more tricky if they drink bad quality water. In the UK we also have problems. This is not only, we have a problem with cryptosporidium. We have outbreaks, very common outbreaks, and normally the water companies, they pay penalties, they pay a lot of money because they have these kind of outbreaks. But cryptosporidium is our personal or challenge in the UK at least. And again, I don't know if you are familiar with cryptosporidium, but the problem is it makes this kind of cyst, and is resistant to chlorine. So chlorine, to be honest, is not very powerful to control all these risks. Climate change. I'm going to tell you what happened with the British, okay? The British make jokes about the weather. And they are always like, here it rains all the time, we don't care about climate change because we have all the water in the world. And it's not true. In London, they have problems to supply water to 8-9 million people living there. They have a desalination plant, for example. And in the UK, we have also problems with extreme weather events like floods and drought. So, yes, they will be affected by climate change. As you can see, flooding before were not that frequent, but now every year we have some like on the news all the time, flooding in the south, in the north of the country, in different places. But we also have drought, so both extremes too. And they were saying in the news that at some point the Londoners, in the future, they are going to need to queue for water. So this is a global problem. It's not just the global south. And in terms of extreme weather event, I think what we really don't know is when we have floods or droughts, how these microorganisms or pathogens can survive, attached maybe to the soil, or how they are washed away and reach our lakes. I think we need to work with people like Maria Teresa to find out the real risk of these things to survive, be alive, and reach our water sources, because there is a lack of information about that. And again, this is for the Londoners again, or for the UK people. You don't have as much water as you might think. In the south of the country, they are struggling. And you were right before. We have a heat wave for this summer in Europe. So also in the UK, they are struggling to have enough water to supply good quality or safe water to all the population. And this was from Sao Paulo, but I'm not going to talk about it because you already talked about the drought in 2014 and all the problems that brought. Cape Town, we are working with Cape Town, and you almost, no? Like a month ago was like, we have 2 days left of water, 1 day left of water, and it was like, oh my God. You reached the day zero, okay. So yes, what I'm trying to tell you is I'm in Europe, but we also have all these kind of problems. It's a common problem. And these are the solutions that, 8 radical solutions for the water shortage that I found from the BBC. The first one that was to try to find new reservoirs, which cost billions of pounds. And in the UK, the water companies, most of them are private, and the idea of spending billions of pounds is a no, no, no. Start drinking salt water. In London, they did. They have a desalination plant. They built it for the Olympic Games. So it's happening already. Drink sewage water. That's a future to be. But I think at some point we will need to treat the sewage water and drink it. Probably not in a few years' time. Persuade people to use less water. Looks like in Sao Paulo it did work. But you need to put penalties and compulsory water meters. In the UK, in my house, I don't have a water meter these days. So I can leave the tap open in my house and I'm going to pay the same every month. So I guess that here you have compulsory meters, but in the UK we don't have. So I think they should be compulsory. Leaky pipes. We saw the talk before about how they deal with the drought in Sao Paulo, but the amount of leaky pipes around in the world are amazing, and the percentages of leakage are amazing. But as I said, the water companies, until they have a problem, they are not going to change the pipe or they are not going to do anything. They were also talking about building a pipe from Scotland to London to feed water to the Londoners, but the Scottish said no. They were not very happy about it. And at some point, if we don't have water, I guess that people will need to move out of London or move to different places. And what I'm trying to do is use all this microbiology that normally the engineers don't interact a lot with the microbiologists, okay? So what I'm trying to do is to make them think about that these are not just infrastructure, it's not a physical structure. There are things living inside that might affect the water quality and they might be a risk for you. So that's why I'm working with engineers trying to work together. And to simulate the climate change, I think there are 3 main scenarios in terms of experiments that I can do to simulate this, which is increases in temperature, problems, addition of nutrients like phosphate or nitrates, but also intermittent water supply. This is a big problem. Pipes that are empty for 1 day, 2 days, 3 days, and then what? When you restart the water in the system, all that biofilm or whatever was there is going to reach your pool water, or people will drink it, but there are not studies about this. We don't know about the risk or what you need to do. And my idea is to use the microbiology to provide tools, risk assessment frameworks, or new biological early warning systems, because the old indicators, I don't really like them that much. But the idea is to provide tools to water companies and stakeholders to incorporate microbial risks in whatever they do. And just to conclude, what I want to say is that that's what I'm telling you, what I'm telling to the engineers, like you can use microbiology to inform risk, and you can really use these methods to design and control and manage your distribution systems. And this is, thank you very much. This is it.
Thank you very much for giving us this nice nice view on water distribution system and the problems that we are currently facing. I guess not only in UK, but in everywhere on Earth. And so the question would here, maybe we can discuss this later. What is the source of this, and how to cope with this? Maybe risk assessment is nice to have the data, to have data from genes as well, but what is the original source? Where is the problem coming from first? Because when you have the piping system, it will not come by itself. That must be have an origin.
They can pass treatment. Treatments are not 100% efficient.
Okay, yeah, well, you can discuss.
The pipes are not sterile and they are not perfect.
Yeah.
So if you have a negative pressure or you have intermittent water supply, maybe a pathogen can go in from surrounded contaminated soil.
I
There are
think
different sources of-
in Germany that this would be a catastrophe when
You have cryptosporidium too.
yes when in official places they talk about pathogens and resistant bacteria in the drink water piping system. That will be a catastrophe in Germany. Okay, thank you very much. Questions later. And I would like now to invite the third presenter to come up here to join the floor. It is Professor Miller Alonso Camargo Valero. He is Associate Professor of Bioresource Systems at the School of Civil Engineering, University of Leeds. And Professor Miller Alonso's research has been dedicated to study nitrogen transformation pathways and removal mechanisms both in wastewater treatment systems, in indoor airborne pathogens transport control, and he did research in the development of algae-based technologies to retrofit existing assets in the water industry to tackle CO2 emissions. And he is working in the area of optimization of the water, carbon, nitrogen, and phosphorus cycles. Well, very interesting, because sometimes we forget that in wastewater systems, for example, we still have some goods. And the recovery of phosphorus is in these days a top theme. Thank you very much. The floor is yours.
Thanks very much for the introduction. I'm very happy to be here in Sao Paulo. I have been in Natal and in Minas Gerais, and every time I go to passport control, it's the only country that really makes me feel welcome. So no questions at all. Yeah, just your stamp and you get into the country. It is very, very good to be here in Brazil. The topic is, or this workshop is about drinking water, and I just want to probably to highlight that we have key challenges as humankind is water security, which is very important, but also we need to deal with other challenges like food security and energy security and all of that within the very big challenge, which is the adaptation to climate change. So my contribution as a water and wastewater engineer is to try to look at what we could do with wastewater and how, by improving the quality of the water, extracting all the valuable resources that we have in wastewater, we can reuse that wastewater safely. We can produce energy. It's possible to recover the nutrients for secure, to achieve food security, and obviously to provide what is needed for public health and to reduce waterborne diseases. If we think about the use of water around the world, is a very clear relationship between what is the economic activities within the countries and what is the type of water that is required. So when we think about water reuse, and we were having some ideas from South Africa, when they have a shower, they collect the water and they use that for flushing the toilets. That's one way of thinking about reuse. But there is many other actions that could be implemented at country level to see how you can transfer that same actions that you do at home at a country scale. For instance, here, for the droughts in Brazil, the option that was implemented was to interconnect the different sources, the reservoirs, so it was possible to allocate water, so to supply water to some areas that probably before the interconnection system was completed was not possible to do that. But at the same time, there was on the news that the governor at that time from Sao Paulo said, why not to have 2 wastewater treatment systems to clean that water and feed it into the reservoirs? And that could be another option just to increase the capacity of the reservoirs that is not going to be fed with rainwater or the water that comes from the natural water cycle, but using treated wastewater. And that perhaps is something that has been always, in my view, a missing element when we are talking about water resource management. When we think about the need for water for agriculture, for instance, if there is a drought, well, there is there is very little that you could do. But if you, even during the drought, you will always produce wastewater. And wastewater must be an element that should be part of the water resource management. And when you account for all the sources from rainwater, groundwater, surface water, you also should account for the amount of wastewater that is produced, because it's a source that you have and can use for other activities. So if we look at this graph, here we identify that the higher the GDP, these are different regions around the world. So we have here Western Europe, Western and Central Europe, and this is the amount of water that is, fresh water that is used for agriculture, and this part is reflecting the amount that is used for industry, and this part is reflecting the amount that is used for drinking water. So if we are producing wastewater that comes from the water supply, that part could replace some of the water that is used for agriculture, or could be used for developing the economy, increasing the productivity in some industries, and so on and so forth. So even when the workshop is about water supply, I want to take a different angle to see how we can contribute to water security by looking at wastewater, looking at how we can improve that. So everybody, when we say, is water a renewable resource? People say yes, because we think about how the water changes in terms of, different from liquid, solid, vapor, etc., under pressure, under current pressure and temperature conditions that we have on Earth. But in my view, the only way that the resource is renewable is if you can use it for specific purposes. So the difference between clean water and wastewater is the distance between your tap and the sink in any house or in any place. And that is a very short distance, probably 20 centimeters or so, but that creates a huge difference between the physicochemical and bacteriological qualities of the water. So we try to identify a very good source, because if the source is not very good, the treatment is very expensive. So for drinking water, we try to identify a source with good quality, we do a treatment, and we bring that water to a quality that we can drink it without any health risk. But after that, we produce wastewater with a quality that is very poor. Around the world, 75% of the wastewater that is produced is discharged into the environment without any treatment. And the only way that we can say with confidence that the resource becomes fully renewable is if we are able to transform this quality and make use of that water without thinking about geological cycles. I know the water will reach at some point in 100, if we are thinking about groundwater, 300 years, will reach the same quality, but we are water is required in high demand. We have growing population, we have urbanization, that is another factor that is affecting how we supply water to all of us. So when we think about water security, probably we don't want to reach this extreme condition when having access to water has to be like that. And this morning, Oscar said that they want to have it not too far, not too dirty, etc., etc. But I think that has to be, first of all, accessible. That's one key factor. Should be enough water, in my view, should be clean, and also should be affordable. Because in many cases we see that those with lowest income are paying the highest amount of the cost that they pay per unit of volume of water is probably higher when you compare with other in the same society when you have people with higher income because of the conditions that they have to get access to clean water. So it's not all bad news when you think about wastewater. There are good components inside the wastewater. We have the nutrients, we have the nitrogen, the phosphorus, potassium, the organic matter that here is represented as chemical oxygen demand, and obviously water. Diverting toilets is a very good idea. Sometimes, in some cases you can apply that, but obviously every single case requires a specific solution that is, has to meet specific criteria according to the needs and the situation that you are facing. But we should consider always that when we present an option for dealing with human waste or waste in general, presenting options that include the possibility to recover resources and obviously try to reuse the wastewater. So in terms of protecting the sources, or going back to water security, it's not only about the quantity, it's also about the quality. And we know that because there is wastewater that is discharged to the environment without any treatment, there are different pathways that could be transporting pathogens to the population. So we know that as a public health engineer, we have the capacity to implement some interventions to disrupt these different pathways from feces to the new host, when we can have the different pathways that will bring those pathogens and create problems to public health. So we have the conditions related to the provision of drinking water, which is important. We have the elements related to hygiene, which is as equally important as the engineering interventions related to sanitation. So I'm going to try to focus on this part, which is trying to provide evidence that we can achieve water security through wastewater treatment and sanitation. So we think about, these statistics probably you are very familiar with. You have about 2.4 billion people that they don't have access to improve sanitation. And that is the statistics that came from the 15-year period that we just passed related to the Millennium Development Goals. We have now the SDGs, and the target is tougher, because we are not thinking about just reducing by a half the population that didn't have access to improved sanitation. We are now talking to providing treatment that is sustainable, et cetera, et cetera. We don't have target yet very clear. The countries they sign the agreement, and I think that many, they don't know what they signed for. So it's still, it is up in the air. We are going to meet the target. It's ambitious, and we hope that we will make progress. We have to recognize it's a huge challenge, because we didn't meet the target for the MDGs in terms of sanitation. So that's a huge task. We know that there are some countries that they are obviously making a huge contribution to these statistics. We know that South Asia contributes to nearly 1 billion people that they don't have access to sanitation. And if we think about open defecation, that is probably a group of 7 countries that they make the majority of the people who don't have access to any facility at all. So the good news is that there are very good examples that can tell us that it's possible to reduce the open defecation, and it's possible to provide infrastructures and sustainable solutions for people who are being affected by the lack of infrastructure in terms of sanitation. So this is also part of the Millennium Development Goals and the huge task to reduce the big gap between the urban and the rural, and obviously to reduce open defecation in urban areas is a challenge. I'm going to use as a reference probably the template that many countries now that they have the economic capacity to invest, they are using. So we always have the idea that the best solution is just to have a pipe that collects all the wastewater. So that means that we provide clean water to every single one, and we have that take it to a specific place. When we do the treatment, we concentrate on removing the contaminants, and we discharge the water with a quality that is accepted by the environmental agency. And who pays for that? The user. And we also think that we need to have a system that collects all the wastewater and take it to a landfill, and in many cases that still is the aspiration for communities that they don't have an infrastructure. We know that this type of approach is not sustainable. We know that many countries that has followed this pattern in the 20th century, they are rethinking the way how they deal with waste, and resource recovery is on top of the agenda of those countries. We are moving far from what we call the linear economy. That means that we are in a specific place, bringing food, water, electricity, and then the city functions as the things that they do, and we provide services of products, and we ended up with waste that is disposed at a very high cost. We need to include that component related to circular economy, where, in my view, I don't see feces as feces. You know, it's strange, no? I see them as carbon that is there. I see them an opportunity for producing fertilizers, an opportunity for producing bio-renewable energy, etc. Composting, exactly. So that is the way how I see waste. And my daughter, she doesn't understand that yet. She's only 10 years old, but I'm going to change her mind. Yes, exactly. The thing is, at school, sometimes the children just talk about what their parents do, and they say that I fix toilets. So in one of the meetings, one of the parents said, oh, could you come to my house just to help me? I have a blocked toilet. I'm sorry, I can't do that, yeah. But it's good that she knows that I fix toilets on a larger scale. That's my aspiration. So we need to know that this relationship between food, energy, and water is there. And that has to be the way how we change our mind. Mindset has to be always trying to correlate these components, how we can reuse the wastewater, how we can produce fertilizers from recovering fertilizers from waste, etc., etc. So in this sense, when we look at the Millennium Development Goals, most of the progress were made on delivering infrastructure. That means that if someone doesn't have a toilet, the idea was we need to provide toilets for everybody. And that was the way how you tick the box and you say, if you reach the population that you want to reach by providing toilets, you met the target. But now the SDGs is all about this value change. It's how we move from the provision of infrastructure, and we now provide some changes in the way how we provide this service and guarantee that that service is sustainable. When we think about drinking water, the target for the MDGs doesn't say anything about the quality, doesn't say anything about if the service is intermittent or continuous. You can have a system that provides clean water, but if that provides water only 3 hours a day, what's the point? Yeah? So there are other elements that we need to think about. To bring an example, I'm going to use Bangladesh. They move very rapidly to provide basic infrastructure to everyone. That helps to reduce health indicators like infant mortality rate or maternal mortality rates to levels that obviously can be improved, but according to their GDP, they have made fantastic progress. If we use the targets that were set and the indicators that were set for the Millennium Development Goals, we see that in the blue area is telling us that in rural areas, 80% of the population, they had open defecation, and by 2015, that was reduced to only 2% of the population. That means that as a country, only 1% of the population is practicing open defecation, which is, I said, that's a fantastic achievement for a country of that size, that 160 million people living there. But that is only a part of the story. Yeah? When we look at how that was achieved, we have the provision of on-site sanitation was one of the measures, and producing or delivering toilets to that number of people requires that has to be, you need to produce toilets at an industrial scale. So they design this type of, the design of the latrines use concrete rings, and they started using single pit latrines, which was a mistake that they realized later, and they moved to twin pit latrines. But still there are many of single pit latrines that they are deployed. They were deployed very rapidly. And what we have here is that the infrastructure is there, but let's say the monsoon comes, the water level rises, the pit is full of water, people, they don't use it. What they do, they go back to open defecation. So you have the infrastructure, but it's not functioning the way that you supposed to use the facilities. And then when we start to look at, okay, what is missing? Why that is happening? First of all, people don't see the need for doing maintenance. There is no provision of the service. First of all, if someone is going to provide that service, it's illegal to do it if you don't have a company, all the insurances, et cetera, et cetera. So what happens is that those who are in the lowest part of the society, you know, they still have the caste system that is inherited from India, and those who are in the lowest income section of the community, they do that type of jobs. Someone who goes into that job lives probably 10 years maximum after that. They sometimes it's very risky because they do that during the night because it's illegal. They can fall into the pit and die. Most of them, they do that under the effect of alcohol, of drugs, because it's not a very pleasant job. So there is a social component that is also linked to that part. And we don't have, sometimes as an engineers, we forget that that is a huge component that we need to look at and try to see how the solution that we provide is related to how the communities will use that type of infrastructure. So in this project, we try to change that condition. We tested different options for doing pit emptying using manual conditions or doing mechanical pit emptying. And we identify, obviously, that there are good components, as we mentioned before. We have nitrogen, we have phosphorus, we have carbon. And the problem is the high content of moisture, because water is very heavy, and if you are going to transport that, it's very expensive. So to reduce cost, you need to do that ideally during the dry season, but people just think that it's important to do pit emptying during the rainy season because it's that when the problems come, so you need to change culture and changing behaviors to improve the conditions for the treatment. And also you need to keep an eye on the environment, the biological risks. We have the pathogen indicator, but also we have other indicators that tell us about the quality of the fecal sludge, including the concentration of helminth eggs, which is a concern if you are going to reuse that as for agriculture. So we take it to a facility for treating the waste, and we were trying to produce a process, to design a process that could take us that to the point that we can produce a product that could contribute to compensate the costs of the entire treatment. Our objective was not, have a company that produced fertilizer. Our interest was to have a system that was able to guarantee that in the future the whole chain functions. Yeah? That means that if someone is making money at the end of the chain, it's because they are interested in bringing the raw material to their process. That means going there, collecting the fecal sludge, take it to the treatment, and then produce fertilizer that could be taken to the market. So after treatment, we identify the different characteristics, and we compare that with the local regulation related to fertilizers, and that is a product that could be used not directly as a fertilizer to compete with industrial fertilizer, but could be used as a new raw source for the production of fertilizers. So that means that we are not extracting phosphoric rock, we are not fixing nitrogen from the atmosphere using fossil fuels, we are recycling, reusing the resources that we have in waste. And that could be used for agriculture. Another example is here in Brazil. Also, Brazil made a huge improvement in terms of the provision of sanitation, and that this project is in northeast Brazil, which is a very dry region. And we were working with colleagues from the Federal University of Rio Grande do Norte in Natal, using low-cost technology, which is the waste stabilization ponds. And the idea was to recover the water and the nutrients simultaneously for the production of food and energy crops. So we tested what the qualities and the, let's say, the characteristics of this system for corn and elephant grass production. We use the elephant grass for the production of these briquettes. Locally, people use firewood, which is affecting the ecosystem. It's very dry conditions, so we are not thinking about the rainforest there. It's not very green. It's very dry, but that ecosystem is very vulnerable because people are using wood for, as a fuel. So it was possible just to have this as an alternative. I'm getting short of time. I think I have just a few minutes. And always the important thing for us is just pass a message to the audience or to the students when we are giving a lecture. So I'm just going to concentrate on that. So water for life, which is very important. Sanitation for dignity. We need to have the options to produce renewable energy for development. And if we want to have sustainable economic growth, we need to focus on resource recovery. Thanks very much.
Yes, thanks a lot for giving us a very nice introduction and overview of the importance of effective sanitation. And I would like to invite the presenters to come up here on stage to answer questions from the audience, please. Just to add the slogan of our Exceed Swindon network, it is too little, too much, and too dirty. Because you mentioned this. Yes, so it's now up to the audience to address and to formulate your questions. Please, who has a question? Over there. Yeah. The mic, please. Over.
My question is for Isabel and for it's about and Alonso, because you talked about this research on sewage and the pipes, and well, if you have a good treatment, a nice network distribution, how can you avoid to have this kind of to avoid this risk, microbiological risk at home? Because if you can, how can you avoid this microbiological because only if we have our own treatment plant at home. And after listening to her speech, my question is about this reuse and treatment for the sewage waste. In which step, in which point can we avoid the microbiological risk? Because we have a composing treatment on the sewage, on the waste, sanitary waste. But probably we'll have to take care about this microbiological infection, little bugs that can come with the sanitary waste. How can we avoid this risk? That's the main question.
The question would, it's better to collect, or would you answer right now? Like to answer. Shall we collect the questions? Or?
Yeah, because I think it's quite different.
Okay.
Then maybe, but it's up to you.
Okay, answer directly. So
I know that some people, they have some kind of filters in the taps and things like that, but they don't change the filter for for like months. So no, because from the filter you can also have this biofilm. I think the water companies and the governments, they need to invest in fixing these leakages, in having a good treatment, and don't compromise public health because they want to reduce costs. That's what happens, at least in the UK. They wait until something happens, an outbreak of cryptosporidium, and then is when they repair the treatment. They spend money in ozone or UV light, but until something happens, they don't improve anything. So I think maybe as a public, we need to push them to take care of us more. That's
okay.
In Rio and São Paulo, probably, we have high temperature, we have difference in change in pressure, and we have the third thing you said, the apport of nutrients from leakage, sewage leakage and things on our water distribution network. So we have all the three variables that could make the situation worse.
Yeah, but the people normally think that is the food, right? We don't have epidemiological data, that's what Maria Teresa was saying.
Yes.
So they normally think that is the food they eat. They don't think.
Yeah, I think the matter is that the main point is protect the water sources. You know, the biofilm is growing, but preparation is not part of a biofilm. It's protected by biofilm because it is in the water source. So for me, protection for the water source is the main point, the key point to protect and promote health. And yes, we have a lack of epidemiological data, so it's hard to make these associations.
So the question was also to you, right?
Yes. In terms of what I would do to reduce the risk of pathogens, thinking about wastewater treatment. I think that the most important part is to reduce direct contact. However you manage to do that. Reduce the risk from the fecal-oral route for the transmission of diseases. Let's say you have a community that doesn't have any type of infrastructure. The first thing is just to provide the type of infrastructure that will contain the waste to reduce the direct contact. The other way is that, for instance, in the UK, we don't disinfect the wastewater. We provide, we protect public health in terms of waterborne diseases by providing good quality drinking water. So that's one part. So that means that you need to protect your catchment that you are used for drinking water supply. And in terms of wastewater, you say that you have good temperature, that you have sun here in Brazil, and that is the perfect combination of conditions for low-cost technology like waste stabilization ponds, that in small localities, that they could use that, and it's the only technology that removes pathogen. We are thinking about highly intensive mechanized systems like activated sludge. They don't remove pathogens in the same way that waste stabilization ponds. Mm-hmm. So the control of pathogens is when you concentrate that material into the sludge, and the control is considering the way how you deal with the sludge. Yeah. Nowadays, the carbon cycle within wastewater treatments has been optimized to the point that you extract as much energy as you can from the sludge, which is when you concentrate carbon. Mm. And in that point, to improve the production of methane using anaerobic digestion, is very common the use of hydrothermal processes to break down the material and enhance the production of methane. And at that point, you reach the inactivation of pathogens, which is obviously the main risk when you are going to dispose the sludge coming from the anaerobic digesters.
Yes, exactly. So there was another question from over here, was it? No? Who was first? Rodolfo, you first? And ladies first? Ladies first. Okay, ladies first.
Thank you. I think my question goes to Isabel. Dr. Isabel, in your speech, you talk about emergent waterborne pathogens, not always associated with E. coli tests, OSCs, for example. E. coli tests in Brazil are the most common tests in order to evaluate microbiological risks. So my question is, how can we use this new approach, as you said, like DNA assays, for example, in order to evaluate communities of microbiological? How can we use this information, this precious information, in absence of appropriated legislation? Because in Brazil we have not appropriated limits of these microbiological aspects. In how can you use this information with stakeholders and politic agents And
We need a good risk. We need
Thank
a
you very
good
much.
risk assessment to prove, because right now we don't have data in hospitals proving that that's what makes somebody ill. But if we can prove it and prove that your E. coli standards are useless because you have 1,000 people in the hospital because sick for something else, that's the only way, I guess. A good, yeah.
First, I don't think E. coli is used to assess risk. It's to assess water quality. And I agree with you. It's far from the adequate. But we have a large country with limitations among the area. So E. coli is still a valuable tool in order to evaluate and maybe to give us some alert. And so but you have good standards. Now we are in the time to review our legislation for drinking water and for sewage sludge utilization. So we are reviewing this, and I think we will have better qualities. And there is a strong recommendation to use risk assessment in this revision. So I think we are in a good track.
thank you so much.
Rodolfo?
Okay, thank you. Well, thank you to all of the speakers. Really nice presentation. I have two questions. Well, but the first one comes with a comment. I come from Mexico City. Mexico City is a very large city that has very particular things like the soil. It's like a jelly, and is an area that is exposed very frequent to earthquakes. With that, I can tell you that since 1985, the problem of leaking pipes and also with the pollution in the clean water, in the fresh water, is very, very complicated. It's not only related that the pipes are very old, you need an earthquake and start to move, and you will have problems. And one of the things is that now, as a tracer, we use, for example, the water quality. When you start to measure the water quality, you can detect where you are having leaking. But at the end of the day, we have something like between, all depends of the year, which year is measured before or after an earthquake. The leaking is around the 30 to 40% of the fresh water. And to give an idea, Mexico City uses around 80 cubic meters per second. It's a river. But the thing that is the solution now, at least in the last 20, 25 years, is to use ozonification for the water. And I think there are no problems with the health of the people. That is incredible. And what is your opinion as a possibility for those places that have to face more or less the same problem? Because to bring water or to try to have water with the quality sometimes is very complicated.
Yeah, ozonation is a solution for a lot of places. The problem is really expensive. That's why it's not used, but it can be a solution. I can tell you something else. The microorganisms, I think they are clever somehow, and they will find a way to overcome ozonation at some point and be resistant in this. The biofilms are really resistant. Ozonation is very good, but at least in the UK they don't use it in certain places because you don't want to spend money, to be honest.
Small equipment for a house is something less than 100 pounds.
So it's a house level, it's not a
treatment level. It's a house level. It's a local solution because it's very complicated when you try to solve in the general pipes, because if you have an earthquake, the problem is not that if you have water or not, the quality is
but
not
who
so
can
good
have access to the ozone?
To drink the water. You have to solve the problem in your own house.
But you need to have money to do that. You need, not all the population will have access, right, to that kind of luxury. I don't know. They can.
Yes.
I don't know.
But at least I can tell you that 80%, 90% of the population in Mexico City has an ozonation system at home. That is a very small, is something like 100 pounds. In fact, in my institute, all the water is treated with this system, and we have clean water without no problems. And to me, look like if you do like in a very large scale, you can negotiate the price with the industry and come down.
Well, that for me is a surprise, because I was in Mexico like 2 years ago and they told me you cannot drink water.
No, you have to pass for the, yes, exactly. But you can discuss this or to talk about this.
A short comment on that. It's very common in Latin America that if you go there, you say, don't drink water from the tap. And at home, it's very common that you have bottled water. And you drink water not from the tap, but from bottled water. In my view, if the system is working properly, having bottled water at home acts only as a placebo. That makes you feel better. So that is the same with some systems that they are installed at household level, like filters with activated carbon or filters with porcelain filters that they are very popular when you don't need it. And the use of ozone or UV radiation could be one of the other examples. But I think when you say that the leakage is telling you that it's a very high % of water that is not reaching the consumer, I would probably challenge that, because in many cases it's not that the water has been leaked through the pipes. It's because there is no way that the water company is actually measuring the water that they are charging. Let's say they have the way to measure the water that they produce, and when they compare that with the water that the consumer pays, there is a gap. There is a difference between these two. So micro measurement is key, because in some cases it's not only the leakage.
Okay. Okay, thank you very much. According to, we are a little bit behind the schedule. If there are still... One more question. Yeah, if there are still one urgent question, one or two, maximum. Maximum. I would like to suggest to continue during the coffee break. So the presenters are still here, and I think the fruitful discussion can be continued then. Okay, two questions, very urgent. Yeah.
Daniel from Santa Maria. One just very quick about this bottled water. The regulation of bottled waters in Brazil is much worse than tap water. So it's strange to see people drinking tap water with a regulation that's, for example, nitrates up to 50 parts per milliliter. And when for tap water we only allow 10. So we allow much more waste, much more pollution in this bottled water than in tap water. So I don't drink this bottled water. I suggest you to read the bottle before drinking. So second part, and this is a question for all, I think I come to these events and I think that the problem is not science in some part, is how politicians address these issues and how we convince them to put all of this stuff that we do in science into regulations and into practical life. That's, I think, it's a point. It's not exactly a question, it's a question to all of us. If someone knows how to lobby for these regulations to go on, how to address these things with local regulation, local water companies, I think it's a good discussion for next symposium, next workshops.
Okay, thank you very much. One question, you.
Okay, my name is Nkeze from the University of Yaoundé 1 in Cameroon. I would reserve my question for Dr. Isabel for another time, but I will have to ask a question that has a link with wastewater and fecal sludge management to Professor Alonso. I'm interested in sustainable development, and when we talk of sustainable development, we talk about cost effectiveness, we talk about time constraint to produce results. In your research, are we considering the possibility of source-separated toilets that warrant fecal feces to go one way and the urine and the liquid part to go another way so that there would be more effective treatment methods and it would be easier to recycle the wastewater? Thank you.
Yeah, absolutely. When you think about the value of nitrogen, phosphorus that you have in urine, and you just jeopardize all of that when you mix it with feces, that makes a lot of sense. The challenge is how you can implement that effectively. If you are thinking about a peri-urban area that you have millions of people there in a very highly dense area, that is a huge challenge. You need to think about something that is applicable. So I'd say that you have to consider all the options, including urine diverting toilets. And you need to use the solution that, as you mentioned, should be the most cost-effective for the particular problem that you have. And going back to the bottled water, if you check the concentrations, also check the units, because sometimes the legislation reports nitrate as N, and the bottled water quality is reported as NO3. So that's sometimes is 5 times higher when you change the units.
Yes, exactly. Okay, thank you very much. Marcelo, I think we have 50 minutes for a coffee break. Is it okay? And after this, we're coming back. You want to give some announcement about what will happen after the coffee break?
Okay, first I would like to thank you for the speakers, for all the contributions. And I would like to say that we have like 20 minutes, and after that we are going to announce the instructions for the people that will keep working during these days in small working groups. We'll give some work to do, hands-on, on the water and shit stuff. And so all of you, of course, are very welcome to stay. And because at the end, by the Friday, we close this workshop, and they have a kind of a product to be developed. So for the session of presentations for today is finished here. Okay? So thank you very much.
Okay, thank you very much from my side to the presenters, to their valuable presentations, and thank you very much for your contribution. So let's have a break now.